All right. So now we've seen how we can do some calculations with the with exponentials and with collections with families of exponential random variables. And so we're now going to talk about we're now just going to do an example involving modeling of an electrical system and the failures in an electrical system. Okay, so here's the idea. So the idea is that we have an electrical system, and the components of the system are connected and interact in a very specific way. Okay. So we have two components. And we'll call them C1 and C2. And the system functions as long as both components are functioning. So we need both in order for the system to work. So maybe the system looks something like this. So there's a component here. Component here, C1. And there's a component here, C2. And something is, you have electric traveling through this in this direction. And so in order for this to work, we need both components to work. And so we're going to suppose that the lifetimes of the components are independent. And we're going to model them as exponential random variables. So that means that they're memoryless. They're going to be T1 and T2 with intensity parameters. Lambda 1, lambda 2, respectively. Okay. And we're going to let T be the lifetime of the system. So the lifetime of the system is how long the system can stay operable before it fails. Okay, so what is the distribution? How do we describe the distribution of T, the lifetime of the system? Well, since we've described we're modeling the system in terms of the two components, and we're modeling the components in terms of their lifetimes, and we're modeling the lifetimes as exponential, independent exponentials. So the lifetime of the system is going to be dependent on the lifetime of the two components. And by the way that we've described this, the system is going to fail as soon as the first component fails. So what that means then is that T is equal to the minimum, right? The minimum of the two. This is notation meaning minimum. We can also just write this as minimum of T1 and T2, right? The lifetime of the system is the minimum of the two. So how can we do this? How can we calculate this distribution? Well, we know of a few ways we can do it, and we'll do both just to make sure that we're fully understanding what's going on. The first is the CDF approach. Okay, so if we let T be some potential lifetime, and we ask, okay, what's the probability now? Do we want to calculate whether the probability, whether the probability of t being less than or equal to t or bigger than t? So do we want to calculate survival probabilities or cumulative probabilities? Well, technically it doesn't matter. You can do it either way because the distribution will be determined by either, whichever you can calculate. But which one's going to be easier to calculate? Well, since we're talking about a minimum, the distribution of a minimum is more easily calculated by considering the probabilities of that minimum being larger than a particular value. And the reason why that is that in order for the minimum to be larger than a particular value, everything in the system, T1 and T2, both have to be larger than that value. Whereas if we were thinking about less than or equal to, just as an aside, so just as an aside, if we were calculating less than or equal to, then this can be true if T1 less than or equal to T and T2 is less than or equal to T, or T1 less than or equal to T, T2 greater than T, or T1 greater than T, T2 less than or equal to T. Okay. And it's just not convenient to have to deal with that, right? And so it complicates it in a way that also allows for the possibility that you might have double counted something without realizing it. So by independence now, this is going to be equal to probability that T1 is greater than T, probability that T2 is greater than T. And by assumption, these are the exponential survival probabilities. So it's e to the minus lambda 1t times e to the minus lambda 2t, which is e to the minus lambda 1 plus lambda 2t. Okay. And the density of this, which is minus the derivative of the survival function, is lambda 1 plus lambda 2 e to the minus lambda 1 plus lambda 2t. So in other words, the distribution, which we've already shown in a previous example, is exponential, and the intensity parameter is the sum of the parameters of the two component random variables. So I think that's the easiest way to go, but everybody has their own opinion and their own preferences. So another way is to do it by infinitesimals. So we can ask, okay, let's say there's a density, then what's the probability, the effective probability of having a death or having a failure exactly at time t? Well, this would be probability that, we'll do it t minus dt at this point. So that t is greater than t minus dt, but less than or equal to t. Well, in order for that to be true, we have two possibilities. It's not possible for both to fail at the exact same time. I mean, it is, but it's infinitesimally unlikely, so we can ignore that possibility. And we say, well, this can happen in one of two ways. Either T1 fails at that instant and T2 lives on after T, or it's T2 that fails in that instant and it's T1 that lives on after time T. In either case, what we end up with is we have something that's, it's a statement in terms of independent random variables, T1 and T2. So what we have is we're going to have the product of the probabilities. So product that T1 is less than or equal to T, T2 is bigger than T, plus probability T1 bigger than T, T minus dt, T2 is in the range, is within dt of T. Okay, and we know what these probabilities are using the infinitesimal approach. So for the first, it's lambda 1 times the width. It's lambda 1 e to the minus lambda 1 t times the width dt, and then e to the minus lambda 2 t. And then plus lambda 2 e to the minus lambda 2. Well, this is in the wrong order. So plus e to the minus lambda 1 t times lambda 2 e to the minus lambda 2t dt. Okay, so we can bring all these components together, and when we do that, we see that this is equal to lambda 1 plus lambda 2 e to the minus lambda 1 plus lambda 2 t dt. And we realize that f of t, the thing that's multiplying dt here, is the density of the exponential, whose intensity is lambda 1 plus lambda 2. So we would conclude here that t is exponential with rate parameter lambda 1 plus lambda 2, meaning that the expectation of t is 1 divided by that rate parameter. How can we relate this? Can we relate this to the Poisson process? Well, we can the component, presumably, once we have once we choose to once the component fails, we're actually going to replace the component, right? So there will be some downtime, but we can ignore the downtime. And we can, instead of just saying, well, the system is going to fail, well, it will fail, but when it fails, we're going to fix it, right? So what happens when we fix it? So what we can actually do is we can model, let N1 be a Poisson point process, PPP, with intensity lambda 1. And N2 be a Poisson point process with intensity lambda 2. So these are counts, right? And N1, the process N1 is independent of the process N2, right? Then we can let T1 well, T1 is the first event in N1, so we know that and T2 is the first event in N2. We know that this is exponential lambda 1. That's how we actually derived the exponential distribution. T2 is exponential lambda 2. But what we're actually interested, though, is we can create a superposition. So superposition process is to define N as the sum of the independent Poisson processes, which by the superposition property of Poisson is itself a Poisson point process with intensity, the sum of the intensities. And T is the distribution. No, T is the first event in the superimposed process N, which by properties of the Poisson is exponential with lambda 1 plus lambda 2. So that's another way to get it. That's another way to think about this. And to see how these ideas somehow are all connected to one another.